Welcome! This is the sketch, organize, solve method for Faraday's law, the loop integral one. And what we'll see is, right, this integral closed of E dot ds looks very, very similar to what we saw a few weeks ago with the closed integral of B dot ds. So we're going to do a lot of things very similar to what we did for Ampere's law, now with Faraday's law. So our first thing in our sketch is we want to draw the magnetic field, which is now our source, right? We're creating electric fields from magnetic fields instead of charge or current distributions from two perspectives. So if we were to look at a thick wire, we'd have, right, a center here, and then we can have a thick wire from a different perspective like this. It's going to have very little field in the center. Maximal field right at the edge, and then the field will slowly drop off. And we can do similar things for the other side. If we're looking at it this way, if the current is coming this way, then we'd have, right, very strong magnetic fields. So actually we should draw them as vectors. And then they will slowly be dropping off. So we have then our magnetic field from two perspectives looking like this, and our Faradian loops, similar to Amperian loops, they can be rectangles or circles. We don't want too many other options for ourselves. And we are going to choose a loop for ourselves where only one segment of the integral E dot ds is non-zero, and that our loop is always perpendicular to the magnetic field. Then we have to do this for each region. So for each region, we want to draw our loop with a different color or dashed lines. So we need to be perpendicular to our magnetic field. And so having an area like this would always be perpendicular. Might look like this in this perspective. So this would be one region in which this is our non-zero segment. This segment is zero because the electric field will be perpendicular to the path. This segment is zero, the electric field will be perpendicular to the path. This segment is zero because there's no magnetic field here, so there won't be any electric field here. We would then need to do another Faradian loop inside. So we could do this one kind of like this. So in our organized step, we've got closed integral E dot ds equals the negative ddt of BdA. So we can kind of split this into our left-hand side and right-hand side. We can do organization steps for both. So over here we have that our closed integral of E dot ds is equal to the integral over segment 1 of E1 dot ds1 plus the integral over segment 2 of E2 dot ds2, and so on and so forth. So what we want to do is we want to justify that only one integral is non-zero, and justify E is constant along the path, and that E is parallel to ds along the path of the non-zero segment. So this should look very familiar as Ampere's law. This should look somewhat familiar to Gauss's law. So if we can say this, then we have our closed integral of E dot ds is equal to just the electric field over our one non-zero segment times delta S over this one non-zero segment for our non-zero segment, which we have to then do, right, 2 different times. For our negative integral of B dot dA, we first want to write our magnetic field as a function of time and space. So in this case, we're going to have a much more complicated magnetic field than what we normally deal with, but that's fine. So we have, right, the magnetic field inside is mu naught I times a variable distance over 2 pi, the radius of the cylinder squared, and this is for r less than the radius of the cylinder. And the magnetic field outside, right, theta hat, outside is going to be mu naught I over 2 pi r for our r less than or greater than capital R. But our current has to also be a function of time, because we have to take a derivative of it later. So we write our magnetic field like this. If we have a solenoid, it's going to be constant in space, which is always nice, always what we want to deal with first. And then what we have is that our integral of B dot dA is equal to our integral over region 1, or region A, of the magnetic field of A, so that might be in, dotted with dA of region A, plus the integral over region B of B sub B, dotted with dA of B, up to the end of the loop. So for this one, we would have this B inside plus the B outside, 2 different integrals. For this one, we end before we get to outside, so we just have the integral of B inside. So then we have all of this, and so we have, right, multiple B dot dAs, 1 for each region. Now, in our solve step, we are going to evaluate our integrals for our integral of B dot dA. And then we are going to take the derivative negative d dt of our B dot dA. And so once we have all of this, now we know that, right, for each region, we have that our electric field at this region times delta S of this region is equal to negative d dt of our integral B dot dA, which is solved, and then we are going to solve for E1 for each region. The good news is this is as hard as it gets for this semester. But the bad news is that now we have functions of both time and space. We have electric fields, we have magnetic fields. It gets a little bit weird, but if we felt good about Ampere's law, this is going to be very, very similar to Ampere's law, just instead of containing currents with a J dot dA, now we're containing magnetic fields with a B dot dA. So that's our only difference. And then we get to find what's going on once we take a derivative of that B dot dA to find our electric